I think we had 33 or 34 last week, so just give it another few minutes. Hopefully I didn't lose too many people after last week. Yeah, I'll just give it another minute. Just less people than last week. It's so same story today. I'll be putting the slides afterwards. I'll be putting the slides in the MB5003 drop down menu on our Sola site where you logged into this class. So if you go down the left hand side of the Sola site, you'll see MB5003 24/7. You drop that down, and I've a subfolder in there called revision slides. So I'll be putting the slides in there after this class. Last week's ones are I put up straight after the class last week. I'll be finishing the 2021 paper today at the bare minimum. We have to get that finished today, and then tomorrow I'll cover question 3. I said today or tomorrow. It'll probably be tomorrow. I'll cover question 3 from the 2022 paper, and I'll also cover question 5 from it. So question 3 from 2022, I just had a look at it there this morning, and it's similar to one of the questions we did last week. You still have to parameterize the curves and all that, but there's two curves. So, or there's two parts of the path that it travels along. So you just have to do them both separately and add the two answers. But I'll cover that tomorrow, and I'll also do question 5 just because it's a bit different to the 2021 paper. That didn't come up in 2021. So I'll do that as well. If there's any extra stuff you want me to try to include tomorrow, you can pop them in the chat, the public chat, or you can click on my name and send a private chat, and I'll write them down, and I'll try and cover as much as I can tomorrow with you. All right, just specify if it's from the tutorial sheet, specify the question, because your tutorial sheets are broken down by lecture and stuff. So just be as clear as you can on what you'd like me to try and do. So that's the story with it. We'll get started today, and question 4 in 2021. So question 4 asks, find and classify all stationary points for the function, and you were given a function. Now, stationary points are where, again, just briefly, that's the first partial derivative of the function with respect to x, i.e. we'll treat any other variable like they're a constant, and that's equal to the first partial derivative of the function with respect to y. So we'll treat any other variables, in this case x, as a constant for that one, where both of those equal 0. So I've just put it, i.e. where both the first partial derivative with respect to x is 0 and the first partial derivative with respect to y is 0. So that's going to allow us to find the stationary points. We deal with classifying them afterwards. So our first job is to work out the first partial derivatives. So, I'll just write down the function. Function is x cubed plus y cubed plus 4x squared minus 4y squared minus 7. So we have to find the first partial derivative of the function with respect to x. So I'm going to treat y as if it's just some number, just some constant. Well, I don't have any y's in the first term, so I'll differentiate that normally, multiply down by the power, subtract 1 from the power. Y cubed is just like differentiating 6 cubed. All right, so if you differentiate, 6 cubed is just a value. So if you differentiate just a value, you'll get 0. I'll write it in just for afterwards. Y cubed will just differentiate to 0. 4x squared with respect to x, differentiated as normal, multiply down by my power, subtract 1 from the power. X to the power of 1 is just x. Minus 4 times y squared, that's like minus 4 times 3 squared, for example. I'm treating it like that. 4 times 3 squared is 36. It's just a value. So that will also differentiate to 0. And minus 7 is a constant. So that will also differentiate to 0. So my first partial derivative with respect to x, I can ignore the zeros. I get 3x squared plus 8x. That's my first partial derivative with respect to x. I'll deal with solving it equals to 0 afterwards. I'll just work out partial derivatives first. And I'll do the y1 over on this side. Again, I'll just take down my function. And now we're going to partially differentiate it with respect to y. So we're going to treat x as a constant. So differentiating x cubed, I'm treating it like 2 cubed. That will give 0. Differentiate y cubed with respect to y, multiply down by my power, subtract 1 from the power. Differentiate 4x squared with respect to y, I'll get 0, because I'm treating x as a constant. Differentiate minus 4y squared with respect to y, multiply down by my power, subtract 1 from the power. And differentiate minus 7, it's a constant, we get 0. So ignore my zeros, I'll get 3y squared minus 8y. Now, to find the critical or the stationary points then, we're going to solve both of those partial derivatives equals to 0. So I'm going to set first partial derivative with respect to x equals to 0, and I'll solve that for x. So solving that, you can use your minus b for, it's a quadratic, x squared. So you could use your minus b formula if you want. A would be 3, b would be plus 8, and the constant c would be 0. There is no constant value there. But we don't have to use the minus b formula. We can just factorize out x out of this. Take out x. And then if two things multiply together and equal 0, well, one of them has to be 0. So we let both of them be 0. So x is 0, and 3x plus 8 equals 0. That's one x value anyway. And the other one, the 3x equals 0 minus 8 is minus 8. So x is minus 8 over 3. So there's two x values for our stationary points. Likewise, we're going to first partial derivative with respect to y equals to 0. Again, it's a quadratic in y, so I could use my minus b formula if I wanted. A would be 3, b would be minus 8, and c again would be 0. There's no constant there. But I can just factorize out y out of this one. 2 seconds. Factorizing out y, and then likewise, if two things multiply to give 0, either the first bit is 0 or and the second bit is 0. And we'll solve that for y. 3y equals 0 plus 8, 8. So y would equal 8 over 3. So for my stationary points now, I'm going to take all combinations of those. So a point is xy, yeah, in brackets. So my xy coordinates for my stationary points, x, so here's x is 0 with y is equals to 0. I'm going to combine all of those. So that's one stationary point. X is 0 with y being 8/3 is another one. Oops. So that's both x equals to 0 points with both of the y's. And now I'll also take x equals to minus 8/3 with y is equals to 0. 8/3, y is equals to 0. And the last one is x being minus 8/3 with y being 8/3. So they are all the stationary points. Sorry, S points. No, I should say stationary, because I don't know if you've covered something called singular points in the module, but there's also something called singular points. So just write STAT points. So they're all my points. We have 4 of them. So that's finding stationary points of a multivariable function. It's not just a single variable. We've 2 different variables in there. That's finding them. We're also asked to classify them. So classifying stationary points, you have a second derivative test. So this is sometimes called the M test, capital M test, but you're using a D operator. They're exactly the same thing. If you Google M test, they do exactly the same job. But this is the approach that I've seen in your solutions as the one that you're taking. So to carry this out, we need to find this D operator, which is, I said it last week, if you see vertical lines around a matrix, it signifies the determinant, right? So squared brackets around a matrix is just a matrix, or rounded brackets is just a matrix. Vertical lines around a matrix signify the determinant. So we're going to need to calculate the determinant of the 2x2 matrix, which is made up of the second partial derivative of the function with respect to x. So we will need to take the first partial derivative with respect to x and differentiate that with respect to x again. We've the mixed second partial derivative. So it doesn't matter which order you take this in, because mixed partial derivatives commute. It doesn't matter whether you take the first partial derivative with respect to x and differentiate that with respect to y, or you take the first partial derivative with respect to y and differentiate that with respect to x. So sometimes you will see that this is fyx, but they're the same thing. Mixed partial, second partial derivatives commute. They're exactly the same for well-behaved functions. So we'll need to find the second mixed partial derivative for here and here, and the second partial derivative with respect to y. We'll take the first partial derivative with respect to y and differentiate that with respect to y again. So we'll need to find the determinant of that. I mean, we can simplify this a bit already. So the determinant of a 2x2 matrix is the primary diagonal multiplied together. Just make it look a bit different. Get rid of the matrix side of it. So that's the primary diagonal multiplied together minus the other diagonal multiplied together. So f of xy, or fxy times fxy. You can write that as fxy to be squared if you wish. All right. So, and then we have these conditions underneath that. So we will be working out those partial derivatives, throwing in the points that we're testing. We'll do each of them separately. So we throw in the 0, 0, I think was a point. So we'll throw 0, 0 into this once we have it. And then depending on what answer we get back, we compare it to all of these 4 conditions, right? So if the determinant happens to be greater than 0, and the second partial derivative with respect to x at the point is greater than 0, then the point we're testing is a local minimum. Do you know what? We'll just actually start, and I'll come back to these as we go through it. So I'll need my first partial derivatives with respect to x and y. So the first partial derivative with respect to x was 3x squared plus 8x. And the first partial derivative with respect to y was 3y squared minus 8y. Just double check that just to be safe. 3y squared minus 8y. Okay, so we need our second partial derivatives. Both of the pure ones, so with respect to x again and with respect to y again, and the mixed second partial derivative. So I'm going to differentiate first partial derivative with respect to x again. So I would treat y as a constant up here. There isn't any y's, so I'll just differentiate it. So multiply down by my power, subtract 1 from the power, differentiate 8x, you get 8. Likewise, the other pure second partial derivative is respect to y again. So there's no x's that I need to treat as constants, so I will just differentiate as normal. I also need the mixed second partial derivative. So it doesn't matter, as I say, which order you take this in. I'm going to take the first partial derivative with respect to x and differentiate that with respect to y. But you could have also taken y and differentiate that with respect to x. So if I'm differentiating with respect to y, I'm treating x as a constant. So 3 times some constant to be squared, differentiate that, you get 0. I'm treating that like 3 times 4 squared. Differentiate 8 times 4, you would also get 0. So the mixed partial derivative is just 0. Okay, so there are second partial derivatives. Now I'm going to plug them in to this d thing up here. So d of xy is given there. So fxx d at some point is, I'll write it down just for the sake of it. Y times itself, you could write it as that if you want. Fxx is 6x plus 8 times fyy, which is 6y minus 8, minus the mixed partial to be squared, which is just 0 squared. So in total, I'll just leave it like this. I won't bother multiplying it out. We'll just leave it like that. You could multiply it out if you wanted. So that's our d that we're going to use to test the points. So one of my stationary points was 0, 0. So I'll test that first. So the value of d at 0, 0, I'm going to be subbing in 0 for x and 0 for y into that d expression. At 0, 0, I get 6 times x plus 8, 6 times 0 plus 8, times 6 times y minus 8, which is 0, 0. I get minus 64. Now, the actual value, the 64 element of it doesn't matter at all. All that matters is that that's negative. So let's go back to these now. If d is greater than 0, that's not the case here. We got minus 64. The second one says if d is greater than 0, that's not the case here. If d is less than 0, okay, so that's where ours falls under. If d is less than 0, then the point is a saddle point. So because we got minus 64, which is less than 0, therefore I can say that 0, 0, that point that we tested, is a saddle point. Saddle. So that's the first point tested. Is a saddle points, is a saddle point. Know that. So that's the first point. The next one that we're testing is 0 minus 8 over 3 or 0, 8 over 3. So we'll test that next. Again, I'll be subbing in 0 for x and 8 over 3 for y. So I'll sub them into my d expression above. 0 goes in for x, 8 over 3 goes in for y. I'm just subbing them in for x and y there in the d expression that we have. So we work that out. 8 times 8 is 64. No, we'll again, like the value of 64 doesn't matter. What does matter is that it's positive. It's greater than 0. So let's see what happens this time. Like it's neither of the last two. That's d less than 0. That's not the case. That's d equals to 0. That's not the case. We definitely have a positive one. If you get a positive d value, you also need to inspect, and by the way, you need to know this slide. All right, you need to learn that slide. If we get a positive d value, all of them greater than 0, we also need to inspect the second derivative with respect to x at the point. Because if that turns out to be greater than 0 as well, it's a local minimum point. If that turns out to be less than 0, then it's a local maximum point. So it's greater than 0. So therefore, we will check the second derivative with respect to x at the point. So the second derivative with respect to x, up there at the top, I already worked that out. 6x plus 8. So I'll be having 6 times x is 0 plus 8. There is no y to substitute in 8 over 3. If there was a y there, I'd sub 8 over 3 in for it. So we get 8. Now that's also greater than 0. So we go back to our table. If d is greater than 0 and the second partial derivative with respect to x is greater than 0 at the point, then that point is a local minimum point. Therefore, 0, 8 over 3 is a local minimum point. I'll just say local min point. That's the second point tested. We'll fit one more in, I'd say, on this slide. So the next one was minus 8 over 3, comma 0. So x is minus 8 over 3. Y is 0. And I'll substitute in those values into my d expression above. So 6 times x is minus 8 over 3. And y is 0. So 6 times 0 minus 8. We calculate that out. We get minus 16 plus 8 minus 8 times minus 8 is plus 64. So again, it's greater than 0. So I need to check the second partial derivative with respect to x at the point. Minus 8 over 3, comma 0. Second partial derivative with respect to x, again, is up there. So it'll be 6 times minus 8 over 3 plus 8. So I get minus 16 plus 8 minus 8. Minus 8 is less than 0. So if d was greater than 0 and fxx is less than 0, d is greater than 0 and fxx is less than 0, then the point is a local maximum point. Therefore, minus 8 over 3, comma 0 is a local maximum point. And we've one more point to test, which was minus 8 over 3, 8 over 3. I'll write out my d again just to be on the safe side. It was 6x plus 8 times 6y minus 8. And I am testing minus 8 over 3, 8 over 3. I'll sub minus 8 over 3 in for x. And 8 over 3 in for y. Excuse me. And we calculate that out. So it'll be minus 8 times 8 minus 64. Minus 64 is less than 0. So going back to our test again, if it's less than 0, you don't need to check anything about the second partial derivative with respect to x. It's just a saddle point if it's less than 0. Hopefully I've done the actual calculations okay there in my head. I'll just double check this one just to be safe. 16 minus 8 is 8. All right. Bracket is 8, and this one here is minus 8, so minus 64. Yeah. Okay, so that's our finding the critical points and classifying them. So we classified them via the second derivative test, and we found them just by first partial derivatives equals to 0. All right, but that slide that I had with the test on it, you need to know that slide. I'll be putting the slides up, as I say anyway, later on. But you need to know that one. To be honest, if I was in your shoes and the likes of that question came up, I think it's a really nice question. There are more complicated questions on the paper. I think this one is practice those, because I think it's not the worst of questions. But I suppose that's all relative at the end of the day. I don't think it's the worst. That was question 4. Is there anything people want to ask on that? No? I'll do the poll like I did last week on A to D with question 4, A being that's no problem, perfect, to D being I was totally lost. How would you feel about question 4? Okay. Okay, good. Okay. Okay. I would imagine, just based on experience, that like if there was a pitfall with it, it's your partial differentiation. Right? Sure, you have to know that slide with the tests, with the second derivative test on it, but partial differentiation, if you're falling down on partial differentiation, practice them. Always visualize the other variable as a constant. Pretend in your head that it's like 4 or 5 or something. I put some videos up on our MLC site as well in that MB5003 drop down menu. In one of the tutorial things that I put up, I put up 3 videos on partial differentiation just as some revision that you might find helpful. Okay. Okay. We'll move to question 5. Now, question 5, it reads a lot more difficult than what it is. It says the parabolic cylindrical coordinates. So these are sigma, tau, and z. Z stays the same traditionally. Are defined in terms of the Cartesian coordinates, Cartesian just being x, y, z, by the following. So we're given the 3 different things. As I said, z tends not to change. Use an appropriate formula from the useful formula sheet. I've screenshotted that in to derive an expression for the determinant of the Jacobian of parabolic cylindrical coordinates. Now, it reads so difficult. To be honest, pronouncing some of those is quite tough. But it's derive an expression for the determinant of the Jacobian. That's what it's saying. You can see that in the formula sheet, the vertical lines, as I said, signify the determinant. And like here's del xyz, and it says UVW. Now I think this is from the other paper. This is from the 2022 paper. This formula, but we're transforming it into sigma, tau, and z. So instead of UVW, I'll be putting in sigma, tau, and z. Right. So, and this is the expression. I'll take it down a bit bigger. It's coming up a bit small. It's del x, del u. So instead of u, I'm putting in sigma. Del x, del v. Instead of v, I'm putting in tau. So del x, del tau. Del x, del w, I'll be having del x, del z. And I'll do that with all of them. Del y del u will be del y del sigma. I'll have del y del v will be del y del tau. Del y del w will be del y del z. And likewise, in the very last row, del z del u will be del z del sigma. Del z del v will be del z del tau. And del z del w will be del z del z. Just replacing them. Now, I don't have the formula sheet from 2021. Maybe what I've just written there, the matrix I've written, is how it was presented in the formula sheet in 2021. I only have the formula sheet from the next year on. So, but look, if it was given like that in 2021, just put in the variables that you're actually working with, sigma, tau, and z. All right. And we have to calculate each of those and fill them into the matrix and work out whatever the determinant is. As I say, I think the question reads confusingly, but we have to take x, which is given to us, sigma tau. I have to partially differentiate that with respect to sigma. I have to partially differentiate x with respect to tau, and I have to partially differentiate x with respect to z. So again, we're gonna, with respect to sigma first. So I'm gonna treat any other variable other than sigma, I'm going to treat those as constants. So I don't have any z in it, but tau, I'm going to treat that as a constant. So I'm treating this as 3 times sigma. If I differentiate 3 sigma with respect to sigma, I would get 3. So if I differentiate tau sigma with respect to sigma, I will get tau. That's the first partial derivative of x with respect to sigma. I also need the first partial derivative of x with respect to tau. So I'm going to treat sigma as a constant. So I'm treating it like 5 times tau. If I differentiate 5 times tau, I would get 5. Differentiate sigma times tau, I would get sigma. The last one I need is the partial derivative of x with respect to z. So partially differentiating with respect to z, I'm treating both sigma and tau as constants. They don't have z's in them. So I'm treating both of them as constants. Treating it like 3 times 5. Differentiate 3 times 5, you get 0. Differentiate sigma times tau with respect to z, I get 0. So they're my partial derivatives of x for the formula. I will then take y, and likewise, I will need to partially differentiate that with respect to sigma, with respect to tau, and with respect to z. So I'm actually going to multiply that in. I think it might be easier if we just multiply it in. So a half times tau squared, and a half by minus sigma squared is minus a half sigma squared. Right, so I just multiplied in that constant of a half into the bracket. I need to partially differentiate that with respect to sigma for the formula. So treat any other variable as a constant. So a half times tau squared will differentiate to 0 because I'm treating tau as a constant. Differentiate minus a half sigma squared. So multiply down by my power, gives me minus 1. Half times 2 is 1. And drop the power by 1, I get sigma to the power of 1. So minus sigma will be my partial derivative of y with respect to sigma. Partially differentiate y with respect to tau. Well, multiply down by my power, half times 2 is 1. So I get 1 tau to the power of 1 is just tau. Minus a half sigma squared, treating sigma as a constant, that will differentiate to 0. So that's my first partial derivative of y with respect to tau. Finally, first partial derivative of y with respect to z. Well, there's no z's in it. I'm treating everything there as constants, so that will go to 0. Now I'll take down z, and again, I'll do the partial derivatives of that. So partially differentiate z with respect to sigma. So, well, there is no sigma there, it's just z. So I'm treating z as a constant. That will go to 0. Partially differentiate z with respect to tau. So again, I'll be treating z as a constant. That will also go to 0. Partially differentiate z with respect to z. Well, that's 1z currently. So if you differentiate 3x, you get 3. If you differentiate 4x, you get 4. If you differentiate 1x, you get 1. So differentiate 1z with respect to z, I get 1. Right? So that's all my information. And now I'm going to plug them into the determinant of the Jacobian formula and work that out. So my x partial derivative, I'm not going to write out that matrix again, but the x partial derivatives go along the top. So I'll have tau, sigma, and 0 along the top. The y partial derivatives, y with respect to partial derivatives, go next. So I have minus sigma, tau, and 0 going in the next row. Excuse me. And lastly, z with respect to the other variables go in the last row. So 0, 0, and 1. Oops. So I'm going to work out the determinant of that. Now, we looked at this as a quick recap on 3x3 determinants the last day, but never hurts to go through it again. I mark a plus, minus, plus along the top. Sure, there are shortcuts that I could take here, but I'm not going to go there. I'm just going to focus on sticking to a consistent method to do 3x3 determinants. So I mark plus, minus, plus. I take a positive tau, block off the row and the column that is on, and I'm going to write down the 2x2 matrix for that, or that remains, I should say. So there's my plus tau. Next, I'll go along and I'll take a negative of the next entry in the first row. So negative times plus sigma is minus sigma. Likewise, I will block off the row and the column that is on, and I'm going to note down the 2x2 matrix that remains. So it's minus sigma is 0, 0, 1. And the last term in the first row is plus 0. So I'll take down plus 0 times, block off the row and the column, and note down the 2x2 matrix. Now, because that's 0 times the determinant, 0 times anything is just 0. So we can forget about that one. But if it wasn't 0 in the first row, if that was plus 5 or something at the end, I'd have to do the whole calculation, all right? So that's the only reason I'm writing it down. But we can ignore that last term. And we'll work out the 2x2s. So plus tau times, whoopsie daisies, multiply primary diagonal together. So tau times 1 is tau, minus the other diagonals together. 0 times 0 is 0. I have minus sigma times 2x2 matrix determinant, primary diagonal multiply together. Minus sigma times 1 is minus sigma, minus the other diagonal. 0 times 0 is 0. As I say, this last one we can forget about because it's 0 times it. Tau minus 0 is just tau, times tau is tau squared. Again, that minus 0 we can forget about. Minus sigma times minus sigma is plus sigma squared. So that's the determinant worked out. Tau squared plus sigma squared. Right, so as I said, I think the reading of this question made it a bit daunting to begin with. But once you took down the formula, it's a case of work out your first partial derivatives, which we did, plug them in to the matrix formula for the determinant of the Jacobian, and work out the 3x3 determinant. Okay. So that's that one. I think it's fair to say though it reads like very heavy stuff. if you kind of filter through it, use an appropriate formula to derive an expression for the determinant of the Jacobian. Write down your formula, work out your partial derivatives, fire them into the matrix, and work out that 3 by 3. Right, so that's question 5. Tau squared plus sigma squared. All right. Questions? Comments? Happy to answer whatever I can. Partial derivative for y. The y partial derivatives, sure. So this one. So I'll take that down again. Now, y originally was half times tau squared minus sigma squared, was it? All right. Now, I could have left it like that if I wanted and do the partial derivatives just using that form. But I just thought it might be easier to multiply in the half first. So half times tau squared is a half tau squared. A half by minus sigma squared plus by minus, and a half times sigma squared. I thought it might be easier just to do it like that rather than having a bracket in there. So I need to partially differentiate that with respect to sigma, because that's there in our formula. We need to find that. So if I'm partially differentiating with respect to sigma, I have 3 other variables. So if I'm partially differentiating with respect to sigma, I'm going to treat tau and z as constants. Treat any other variables other than sigma, I treat them as constants. So this is like a half times, I'm treating that in my head like a half times 4 squared. If you differentiate a half times 4 squared, which is just a number, I will get 0. That will go to 0. A half times sigma squared, so that has a sigma in it. What do? We multiply down by the power. So it's a half times 2 will come down, and I subtract 1 from the power. So there's no other terms. 0 we can forget about. Minus a half times 2 is minus 1. Sigma to the power of 1 is just sigma. So minus sigma we get for that one. We move on. We partially differentiate y with respect to tau. So again, if I'm differentiating with respect to tau, I'm going to treat sigma and z, if they're in it, I'll treat them as constants. So looking at y, it's a half times tau squared. Tau is the variable in question. So I'll multiply down by my power. 2 will come down, multiply down by that, and subtract 1 from the power. Minus a half sigma squared. Sigma is one of the ones I'm treating as a constant. So it's minus a half times 5 squared, for example. That's just a number. So that would differentiate to 0. Half times 2 is 1. So I get 1 tau to the power of 1. 0 we can forget about. You can write 1 tau to the power of 1 if you want. The last one, partial derivative of y with respect to z. So if I'm differentiating with respect to z, I am going to treat sigma and tau as constants. So half times tau squared is like a half times 5 squared. That will differentiate to 0. Half times sigma squared, treating sigma as a constant, it's like minus a half times 3 squared, for example. That will also differentiate to 0. So they would be my second partial, or my first partial derivatives of y with respect to sigma, with respect to tau, and with respect to z. Anything else that I haven't kind of made clear for you? Right? Anything else on the question? Anybody else? Or No. Okay. Look at question 6. I think somebody asked as well last week, could we go through a question 6? And there is no way I would leave out the likes of this. So 6a says, using the Cartesian coordinate system. Cartesian coordinates is x, y, z. X, y, z are the Cartesian coordinate systems. So set up, but do not evaluate the triple integral that would be used to evaluate. So the triple integral there, E is the region in question. I'll talk about that in a sec. We have this scalar field here, term there, dv, where E is the region. So we're being told now what this region is, where E is the region bounded by the xy plane. So on the graph given, right? Z is the vertical axis almost all the time. That will be given as the vertical axis. The xy plane is that flat surface down here, all the boxes in it, that the x and y axis both sit on, basically. The xy plane is like a sheet of paper. It doesn't have any height, like I know a sheet of paper does, but it's this flat sheet of paper, literally, that the x and y axis both sit on. So it's a flat surface, flat horizontal, usually horizontal surface. So E is the region bounded by the xy plane, so that flat surface with all the boxes in it, and the paraboloid. So that's this kind of cone-looking shape given. It's not a cone, but it looks like a cone, as shown in the graph below. So we know that it goes up as far as z is equals to 4. That is the square-looking plane, the gray kind of square thing. So it's all of the region below this, so underneath that, and above the xy plane. Right, so that's the region. That's E, is what's coming up on that paraboloid above the xy plane and below z is equals to 4. Right, that's the region in question. Now, how do we go about setting up this integral? The first piece that I'll take care of is the vertical piece of it, the vertical section of it. So I'm going to change this. I'll say it's an inner integral, inner meaning the most inside bit. I'll change the inner integral. That's going to deal with the height component of it. And then I'm not going to worry about height anymore, right? So I'll leave the two outer integrals and I'll call them, I won't call them E, I'll just call them a different region for now. I'll call them R and I'll come back to that. But it's not E. E is the whole 3D image. But I'm going to change this inner integral to take care of the height element of the graph, let's say, right? So I know Z goes up as far as 4. So that will be the upper limit. That's how high it goes up. And all the other Z values underneath are defined based on x squared plus y squared. So all the other ones below that will be x squared plus y squared. Right, so Z, no matter where I am on that graph, like here, for example, x is 1 and y is 1 at this point, the Z height for that, very hard to see, it's just a screenshot. That point there on that curve will be given by 1 as well. It's hard to see there, but Z would be 1 squared plus 1 squared, giving the corresponding height. So all of those Z heights on the paraboloid the whole way around are based on I square the x, I square the y, and I add them up, and that will give me the height. That will give me the Z. So they would be the limits for the height component of it. I have my term here. Sorry, oops, I nearly missed that. That's 3/2. And dV is a volume term. So I have to put dz there because my inner integral now is in z. This. So dz has to be the inner term on the other side as well. And instead of volume, instead of dV, when I've taken a height element out of it, I'm now just talking about area being left. So the height element is satisfied. The inner integral and the dz are the height. So they're taken care of. If you imagine a square or a cube, sorry, don't have any cubes here, do I? Don't think so. If you imagine a cube, and if you take the height element out of it, you're left with a square. So you're left with the area, not the volume of a square, you'll be left with the area of a square. So what you will see in your lecture notes and stuff is that now changes to dA, because the height element is taken care of with dz. Z is the height. Right? So that would be my first venture into writing this using the Cartesian system. First, I'll take the height element, which is the z. Next, I'm going to have to deal with x and y. So I think I have this again here. I do. Okay. So I'm actually going to move to the next slide. I'll write down that integral again, as far as we made it. And z was x squared plus y squared up as far as 4. These are tricky problems. Squared plus y squared to the 3/2. They take a bit of thinking, to be fair. dz and a is the area. Now, which brings me back to this. Or, said I haven't called it E because E is that three-dimensional conic kind of section. Or is the region where height is taken out of it. So if we look down on this shape, we say that we project. See, that's kind of, I'm terrible at drawing, but like that's where that plane intersects the conic. This plane here intersects the conic. So what we say is we're going to now project that down, that blue circle I've drawn. We're going to project that down onto the XY plane. It's like we're looking down on it. The height gets taken out of it. If we look directly down and project that onto the XY plane, I'll draw that a bit bigger. Hopefully that kind of taking the height out of it. It's not a very mathematical sentence, but hopefully it kind of registers as somewhat making sense. If we take that blue circle and project it down, we will get a circle. Now, that circle will intersect the x-axis. This is actually this one, but it doesn't really matter, right? It intersects the x-axis at 2 and -2, because I know z is 4. So this definitely intersects when z is 4, and if z is x squared plus y squared, it will intersect when x is, like the y value is definitely 0 on the x-axis. So 2, 0 would be a point, because 2 squared plus 0 squared is 4, and -2, because -2 to be squared plus 0 squared is 4. And this is our y-axis. So R is that region, that circular region. We're told that z equals, well, the circle centered at 0, 0. So x squared plus y squared equals to 4 will be the equation of that. So any circle centered at 0, 0 that's the equation of it. That's the formula for a circle centered at 0, 0. And our radius there is 2 of that circle. Right. So to convert this to Cartesian coordinates, well, this is a long process. I mean, when you're sitting down doing an exam of this might only take a minute or two, but to explain it takes quite a while, is to convert this area back to X and Y. The Z I've taken care of, I have dZ, but I need to convert dA into something that deals with X and Y. Well, area is just X times Y. So I'm going to leave this inner integral. And I'm going to try and convert area into dy dx or dx dy, whichever order. There's no real big deal around what order you take it in, as long as the limits on the other side, like if z is first here, z has to be the inner integral. If y is next, my next integral here will have to be y equals. And lastly, I'll have to have x equals, right? So y equals, well, if x squared plus y squared is 4, I can solve that for y. I know the x values are between -2 and 2 in that region. So x is -2 up to 2. When I projected that top of the conic down onto the xy plane, the x values are between -2 and 2, right? Y, I'll be able to solve using this, because that will give me the y values in the region. So x squared plus y squared is 4. But y squared equals 4 minus x squared. So y itself would be the square root of 4 minus x squared, but we're looking for an upper and a lower limit. So I'll say plus or minus. You know, when you take square root of something, square root of 16, let's say being plus or minus 4, I'm going to take the plus or minus here. So y will be from minus root 4 minus x squared up as far as plus the square root of 4 minus x squared. But that would be the triple integral converted to Cartesian coordinates. I started off, let's track through it again, because there's a lot in this, right? So we started off with a region E, which was that three-dimensional region between the z is equals to 4 and the xy plane of the conic, and a volume term here at the end. So the first thing that I attacked with it was the height element of it, right? So that inner integral, we had z limits. I know it goes up as far as z is equals to 4. That's where that intersects with the conic, would be on z is equals to 4. So that would be my upper limit. And all the other z values underneath that are given by x squared plus y squared. So they will be all the values underneath 4. Because I've set up the inner integral, the most inside one, the most, as we read it from left to right, let's say, the most inside one, that has to change to dz. That's the height component of the integral. Once I remove height from a surface, as I said, silly example, if you imagine a cube, and if you remove the height of the cube, you're left with a square. That becomes area, is what's left over. And then I've changed the region. Instead of E, I'll call it something else. Let's say call it R, because it's no longer E, because I've taken out that height of it. So now we have to deal with, well, the A, I want that now in terms of X and Y. So I want dy dx or dx dy, whichever. And this region, I'm going to have to work out the limits for both of those integrals. So we project the E downwards onto the xy plane. So I imagine just looking down where it intersects with z is equals to 4, you'll get a circle where the x values go between 2 and -2. So I said dy dx. So x will be the outer one between -2 and 2. And the y will be given by this here. I think a valid question here would be, well, if it's a circle, why does y not go between -2 and 2 as well? And you only want, traditionally, you only want specific values like 2 and minus 2 on the outer integral, the furthest one to the outside. So you'll see that my integral to the furthest left here has specific values on them. Whether the other ones, sure, I have up as far as 4, but the other ones are in terms of the other variables. Okay, so to find the y limits, I take the equation of this circle and I solve it for y. All right. So now I have dz would be the inner integral, dy would be my next integral, and dx would be my last integral. As I said, there's quite a bit in that. That's part 6, part A. So I'm totally suggesting to you to ask questions on this. It's heavy enough. Anything? I actually think that 20. Yeah.
Sorry, in the solutions that we have, it just says that I'm making the assumption here that you can ask your lecturer that I think the question should have asked for the region bounded by the plane z is equal to 4 and not the xy plane. Would you be able to do it that way as well, just so we have both?
Can you say that again? Sorry.
Sorry, it says that in the solutions that we have, that I think the question should have asked for the region bounded by the plane z is equal to 4.
Yeah.
Not the xy plane. I was just wondering, could you do it that way as well? Just so we have an idea of both, if that would be okay.
Can I do it with z is equal to 4? In my opinion, I think that should have said bounded by the xy plane and z is equals to 4. That's pretty much what I've done there.
Okay.
All right. That's pretty much what I've done. Okay. And we haven't evaluated it yet. Obviously, that's coming up, I think, in part B, if I remember correctly. Yeah, change of variables. So this will be in cylindrical coordinates when we go changing it. Essentially, because I can see there's x squared plus y squared in it. And the cylindrical components, or the cylindrical coordinates, are defined. You actually have it. It was given in the formula sheet in this specific one. If you have questions on that, further questions, please do ask. But this is straight from the formula sheet. So because my integral has x squared plus y squared in it, I'm going to use that because that's just r squared. If it had an x squared plus y squared plus z squared, I'd use spherical coordinates. But I'll use cylindrical here. Popping the sorry, would you mind popping the question back up? No, it doesn't say that it goes through 0, 0. It doesn't say that, but we know it goes through 0, 0 because if x and y are both 0, the height is 0. So 0, 0, 0 is definitely the bottom point on that. If the z value was equal to 2, okay, if the z value was equal to 2, would that mean the x values? Let's have a look. Oops. So if the z value was 2 down here, and not necessarily, like if z is 2, so I'll just put this as an aside. Whoa, this as an aside down here. If z was 2, if I'm grasping your question correctly, right? If z was 2, there's a load of different x's and y's that I can have that would make it equal to 2. There's an infinite number of x's and y's because z is equals to 2 on this conic thing. Z is equals to 2 intersects there in a circular shape. So z is equals to 2. You picture like the z is equals to 4 is that flat surface. Z is equals to 2 would just be another flat plane lower down. So along that, we have infinite points along that circle that are gathered from x-axis is this one. Like, let's say here, and the y value here, x squared plus y squared might give this one. This y and x, if I square up each of them, it might get that point there. Like, there's an infinite x's and y's. We don't know that they're both just plus or minus, but maybe I haven't grasped your question correctly. Are you asking about the bottom, this thing here? If that was 2, that number 4 there, if that was 2, see? If that is your question, then absolutely. Okay, cool. But yeah, if that was x squared plus y squared equals to 2 in this equation, then absolutely x will go between minus root 2 and plus root 2. Yeah. Because that's the equation is equal to 4. I mean, r squared is 4, so it has to go between 2 and minus 2. Okay, so we'll plow on with it. I'm going to use cylindrical coordinates quite simply because that's how our integral looks. I'll write it down again. Now, I recommend knowing this, to tell you the truth. Like, dA is dx dy. As we've already done. Remember, we converted dA to dy dx or dx dy, whichever. It doesn't matter what order you take these in, as long as the limits on your integral correspond to the right hand dz, dy, dx we have. So it has to be z, y, and x limits on the integrals in that order. I would know that. It's not in this, but I don't know. I learned that at some point, and it's fine to just know that off. That dA is dx dy. We've already done that bit. But instead of dx dy, or instead of dy dx, whichever order, we can substitute in r dr d theta. And I would just know that. So for our cylindrical coordinates. So I'm going to take down my integral again. It was x squared plus y squared up as far as 4. The next one was y minus 4 minus x squared, 4 minus x squared, the roots of those, minus the square root of 4 minus x squared as far as square root of 4 minus x squared. And the last ones were x between minus 2 and 2. Then we had x squared plus y squared to the 3 over 2. Then we had dz, dy, dx. And again, I'll just stress z should be the inner integral, y should be the next limits, and x should be the last limits, if I'm organizing it in that way. If you want to change around the order of dy dx anyway to dx dy, go for it. And just make sure that the x would be the middle integral. You have x limits there and y last. All right. So that's our setup essentially. I'm going to use cylindrical coordinates because of that. That's just going to be r squared. I have a dz, which I'm going to leave. Dy dx is r dr d theta. So I can change that to r dr d theta. X squared plus y squared to the 3 over 2 will become r squared to the 3 over 2. And we'll figure the rest out from there. Right? So I have my 3 integral signs. Instead of that, according to the formula sheet, that's just going to be r squared. So I can pop that in, r squared. That's to the power of 3 over 2. dz, I'll leave. instead of dy dx, know that that is r dr d theta. So now it comes to, well, I need to change the limits on the integral. So z was x squared plus y squared. But now in cylindrical coordinates, I know that x squared plus y squared is r squared. And z goes up as far as 4. Right? So that's z. I've just converted that to cylindrical as well. The next one has to be, so dz taken care of. dr, so the next limits have to be r. R is your distance from the origin, which is between 0 and 2. You go back, distance from the origin, 0 to 2. That would be my r limits. R is equals to 0, up as far as r is equals to 2. The last one that I need to take care of is theta. Well, it's a circle. That whole region goes around in a circular pattern the whole way up. So theta will go between 0 and 360 degrees, but 2 pi. We work in radians. So there will be my theta limit. And I'll take down that, and I'll just simplify this a bit, because I've r squared to the 3 over 2, and I have another r here thrown in, so I need to combine those so that I just have dz, dr, and d theta together. So theta was between 0 and 2 pi. That's circular nature. R was 0 to 2. And z was between r squared and 4. Yeah, and I always recommend, you really should write z equals, at least on the lower limit. You can write them on both if you want, but r equals will be the next one, and theta equals on the last one. And that's solely because you know then what limits they correspond to when you're going subbing them in afterwards. So that's our limits set up. We have r squared to the 3 over 2. And remember, there was another r there. When I replace dy dx with r dr d theta, there's another r to include. And r. And we had dz, dr, and d theta. So I'll simplify this. R squared to the 3 over 2. So one of your rules of indices is, if you have something raised to a power that's raised to another power, you multiply the two powers. So 2 times 3 over 2 is 3. That term is r cubed. R cubed times r to the power of 1 is r to the power of 4. So all of that r stuff simplifies to r to the power of 4. dz, dr, and d theta. So that's our limit set up. The scalar field is tidied up a bit to r to the power of 4, dz, dr, d theta. So now I'm going to start integrating it. And we integrate from the inner integral out. So I start my integration with this integral. I'm integrating with respect to z. So when I'm, just like with partial differentiations, remember, if we're integrating with respect to one variable, we treat the others as constants. When I'm integrating with respect to z, limits for y, how did it become? Sorry, that's not y, that's r. So r is the distance from the origin to a point. So when we looked down on it here, r, the distance from on that projection to the point is 2. So it goes from 0 to 2. And again, all of this should really be shaded in, because when I looked down on this and projected it downwards, like this point would also be in there. This point would also be in there, etc. So that really should be a shaded region. So the distance from the origin to any point is from 0 to 2. That's what r is. So remember, I changed them from a Cartesian system to this cylindrical coordinate system. That's what r from 0 to 2 is about, right? But when I'm integrating with respect to z, I'm treating the other variables as constants. So I'm treating this like some constant to the power of 4. If you integrate some constant with respect to x, you get 3x. If I integrate r to the power of 4 with respect to z, I'm going to get, with respect to z, I'm going to get r to the power of 4 z. Just like 3 with respect to x goes to 3x, r to the power of 4 with respect to z goes to r to the power of 4z. So I'll leave my outer integrals, because as I say, we integrate from in to out. Leave both of them. Integrate r to the power of 4 with respect to z to get r to the 4z. And I have limits for that. Just put this in a little box. I have limits to substitute in there of r squared for z and 4 for z. This is what I was saying when I was on about the, I still have the rd theta at the end. This is what I was saying when I was on about writing down z equals and r equals and theta equals, is because if I had this, I wouldn't be so sure of which ones to sub in r squared and 4 for. Whether when I wrote down z equals, I know r squared has to go in for z, because that's what z equals, and 4 has to go in for z. That's what z equals. All right. How do you find the r and z limits again, please? Yeah. So I might just finish off this little bit, and then I'll go back to the limits again. All right, if that's okay. I'm not going to do the very last integrals. I'll leave these other 2 integrals, and I can go back after I've tidied this up a bit, and we can go through the limits again. Oh, substituting in limits. I've done the integration, so I'm not writing another integration sign here. Substituting in limits, we sub in upper limit, and again it's z, so it will go in for z, upper limit, minus substitute in the lower limit. So the lower limit goes in second. So we have r to the 4 times, substitute 4 in for z, r to the 4 times 4, minus r to the 4 times, now r squared is going in for z, r to the 4 times r squared. Still have the rd theta at the end. I will tidy up what's inside that bracket now. It mightn't be any harm to go through the 2022 question 6 tomorrow. It's very similar. But 2 and r to the 4 times 4 is 4r to the 4. And r to the 4 times r squared, do 2 of the same base, you keep the base and you add the powers. So r to the 6 minus r to the 6. And I still have dr and d theta left at the end. Okay, so before we go through that, I'll just go back to the limits. Excuse me. So this was where we left it off from the Cartesian coordinates. We're here, right? So that was kind of like, did I take that down? I did. So it's here. That was where we left off the Cartesian system, was there. And then we're going changing it to cylindrical coordinates, right? So in the formula sheet, r squared is given by x squared plus y squared. So where z was x squared plus y squared as a lower limit there, well, x squared plus y squared is r squared. So z equals r squared would be the lower limit for z in terms of r and theta. Right, so that's just replacing x squared plus y squared with what it is from the formula sheet. Likewise, x squared plus y squared in here can be replaced with r squared. That gets replaced with r squared. I still have my power of 3 over 2. Now, in the cylindrical system, z equals z. So z stays the same. So this dz will stay the same. instead of dy and dx, I do advise just knowing that dy dx or dx dy is r dr d theta. So instead of both dy and dx, they can be replaced with r dr d theta, right? So z goes up as far as 4, so z goes up as far as 4. Now, once I change, so as I said, dz stays the same because z equals z as given. So I still have z equals. Sure, I changed x squared plus y squared to r squared because I'm getting rid of x and y, right? I'm moving from the Cartesian system to the cylindrical system. So that's why x squared plus y squared gets replaced with r squared. Once I replace these, so I still have my z limits, as I just said there. The r, so I need my next integration sign, as I read from right to left, the next one over, has to be r equals. So r, I don't know what kind of formulas are we given for these. Like r is, well, it's the distance from the origin out to a point. So if you project that down, remember we did a projection? We looked down on it. But r is the distance from the origin out to any point. As I said, all of this region is shaded here as well. So r could be this distance, r could be this distance, r could be that distance, but it's only up as far as r is equals to 2. That's a circle of radius 2. So the r possible distances will be either at 0, will be literally that point down there at 0, 0, 0. So the distance from the origin could be 0 up as far as 2. So they would be our r limits from 0 up as far as 2. I wonder, out of interest, is the 2022 paper you weren't given a graph. We might have a look at that tomorrow. Probably be as well off sketches and stuff like that. But they will be our r limits. The last one is theta. So the very last integral to the left has to be theta equals. So a circle goes between 0 and 2 pi. So for these limits, because again, I should bring it back, I suppose, to the overall thing. Remember I said that when we started, when that integral was there, that's the height taken care of. Right? That was the height kind of aspect of it. Once we work out then, and we start looking at these two, we're just looking at the projection down. So this one here. R is the distance from the origin. Distance, so distance is not going to be negative. R will go between 0 and 2. And theta is the angle around. So a circle from 0 to 2 pi. You can go from 2 pi to 4 pi if you want, or whatever. But they would be our limits for that. Does that help at all? First and foremost, we're trying to get rid of x and y. Okay. I think we'll do. I'm going to add in that other question 6 tomorrow, because it's tricky. But that's where we're at with it. Work down as far as there. Next, I'm going to integrate with respect to r. So with respect to r, I'm going to treat z and theta as constants. There isn't any z and theta in this, so I'll integrate it normally. So I'll leave my outer integral. And I'm going to integrate now with respect to r. So standard power rule of integration, add 1 to the power and divide by the new power. Add 1 to the power, divide by the new power. And my r limits are 2 and 0. Done that one, I still have d theta left. It will be my last integral to do. I know r is equals to 2 up as far as, or 0 up as far as 2. So I'll sub in my upper limit minus my lower limit. The integration done for it, so substitute in my limits. 4 times upper limit is 2. minus the lower limit of 0 and d theta. So that's all just 0. It's all going to be gone. So the first one, value for this, 256 over 35. If you calculate that out on a calculator, you get 256 over 35. Actually, write this on the next slide. Theta equals to 0 to 2 pi. I said all of this bracket here is 256 over 35, and I still have d theta at the end. So now I have to integrate that with respect to theta. Integrate a constant with respect to x, like 3, you get 3x. Integrate this with respect to theta, I'll get that times theta. 3, 2, 2, 5, 6, 35 times theta. And I have limits for theta of 0 and 2 pi. So I'm going to substitute in my upper limit for theta. So I'll have 256 over 35 times 2 pi. Minus, sub in my lower limit of 0 for theta. Anything times 0 is 0. 256 times 2 is 512 for 35. And there's a pi there as well. So that would be the answer to that one. All right. Yeah, there's quite a bit of work in that. I think try and get your head around first and foremost the like splitting up the region into Z, Y, and X. And then selecting, as I said, I selected cylindrical here just because of the way it looked. There was an x squared plus y squared in it in 2 places. So I knew they could be replaced with r squared. If we look at the 2022 paper, yeah, I mean, again, Cartesian, it's asking you to use Cartesian coordinates first and then an appropriate change of variables. And if you look at the 2022 paper, again, there was an x squared plus y squared. So I'd go down the road of cylindrical coordinates again for that one. Could be really worth your while. Spend time on question 6 from 2022 this evening. Try and figure it out and try and convert it and integrate it. It would be really good practice. Sometimes these type of things, when you first start doing them, you need to really stick with them and struggle through them, to be honest. Question 5. So, okay, so tomorrow I am going to, I was kind of thinking of doing question 3 if I had time today. I went overtime last week. Tomorrow I'm thinking question 3, 5, and 6 from the 2022 paper. I might get you started on 3 today. I'll stay an extra 10 minutes or whatever. We'll get started on 3. It's a line integral, just a single integral around the path C. Single integral around the path is what's called a line integral. It's a line integral, which we did do in this paper in 2021. It came up in question 3. Yeah, question 3B part 2 was a line integral question where we parameterized the curve. However, in 2022, there is 2 curves along the path. There is a line segment followed by a portion of a circle. So I'll just pull that up. We'll do the parameterization of them today. We'll finish it tomorrow. But I just want to get you started on it, and then from the point where we parameterize it, it essentially becomes the same as the last one. But I haven't covered parameterization of a circle with you, so I can find I left a lot of blank slides on this at the end. Right, that was it. 2022 question 3. So it's the same starting idea anyway as what we did in the in the 2021 paper. Put it up. Okay, so C is the curve along what we're following. Actually, let C be the path, right? But here, unlike the 2021, in 2022, there was two paths. Well, the path was made up of two different things. So we're going to need to parameterize both of them separately and see the overall curve. Let's say I'll call the line segment C1, curve 1, and I'll call the circle curve 2. The overall curve, C, is made up of the union of both curves. Yeah, if I draw some line followed by some portion of a circle, the overall curve is made up of C1 as well as C2. We union them. In terms of working this out, we would work out the line integral for C1, omega xyz. We would work that out, and then we would add the answer to the integral around C2. So we're essentially going to do what we did the last in the 2021 paper. We're just going to do that twice and add the answers together, right? So we parameterized the line segment the last day, but we can go through it again. So for the line C1, which is I'll just write line seg. Remember as well, it says line segment. So we're going to have to give start and end values for t in the parameterization. So the line segment is, in vector form, is R0, which is some point on the line. I'll use 1 minus 3, 2. Plus t times the direction. The direction is given, remember, AB, vector AB is B minus A. So the direction vector would be the end minus the start, let's say. So 0 minus 1 is minus 1. Minus 6 minus 3 is minus 6 plus 3, which is minus 3. And minus 1 minus 2 is minus 1 plus 2, which is 1. I will simplify that a bit more. So we have 1 minus 3, 2, plus t times minus 1 is minus t. T times minus 3 is minus 3t. And t times 1 is t. And we'll just add up the corresponding components. So 1 plus minus t is 1 minus t. Where am I? Minus 3 plus minus 3t is minus 3 minus 3t. And 2 plus t is 2 plus t. Oh, that is an infinite line, so we're going to have to give the t values corresponding to the start and end points of this line. So I know at the start, which is the easiest one now to pick. Probably go with the last one. So for the start t value, at the start, I want the 2 plus t to equal minus 2. The last component has to equal minus 2 at the start. So 2 plus t has to equal minus 2. So, not right. Oh my God. Minus 2. My bad. In the question, it wasn't plus 2, it was minus 2. Minus 2. So minus 2 plus t has to equal minus 2. So t has to equal minus 2 plus 2, which is 0. So I know the start t value for this parameterization is 0. The end t value, so as this line tracks along, I want the very last point of minus 2 plus t to equal minus 1. End, not end. So t, it goes up as far as minus 1 plus 2, which is 1. So there would be my parameters for t. Now we worked that out the last day. We worked out the line integral then from that in the question from the 2021 paper. But I do want to talk to you about parameterizing then the circle, because we're going to have to do this line integral along the line segment, same as what we did in 2021. But we also have to do this one. And the second part of this path is the circle. So if you have a circle, x squared plus y squared equals r squared, and z equals, I'll just say z for now, just the height element of it, how the circle is moving upwards, let's say. So we parameterize it as r cos t, r sin t, and z. So r being, circle is r squared, like here, x squared plus y squared is 36, is the circle. So r squared equals 36. R squared is 36. So r is 6. The radius of the circle is 6. Square root of 36 is 6. So the parameterization of this circle, in this case, r is 6. So 6 cos t. R is 6. So 6 sin t. And whatever the z value is, I'm told z is -1. So that would be the parameterization of the circle. However, it's a portion of a circle. So again, we need start and end points. So I'm just going to talk through about how to work those out. So C2, and I'll write it down on 6 cos, 6 sin, and -1. But we do need start and end points. So la 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 la. It says the portion of the circle traversed anti-clockwise from this to this. So it's those points are on the circle and it's just moving along those from one to the other. So the start point is 0, -6, -1. What's the other one? 3, 3 root 3, and -1. Like you'll see in both cases there, the z value is -1 because z is always -1 along this circle. So the -1 values we can just kind of ignore for now. I need to find the t values for the start and end of it. So at the start, 6 cos of t to equal 0. And 6 sin of t to equal -6. Whoops, 6 sin of t. And we're going to solve those simultaneously to find the starting point. So cos of t equals 0 divided by 6, which is 0. And sin of t equals -6 divided by 6, which is -1. So if you solve both of them, you'll get pi over 2. But, sorry, if you solve this, you'll get t is equals to cos of 0. Your calculator will tell you that's pi over 2. But if you solve this one, get t is equals to the inverse sine of -1. You get minus pi over 2. Your calculator might say it's 3 pi over 2. But the answer to this is minus pi over 2 as a starting point. Because you might remember, like, sure, a coordinate is xy, but you can represent a coordinate as, this is just 2 dimensions. It's like cos t sin t. Like, what we're saying here is when cos of t is 0, the x part is 0. The x part is 0. That's why pi over 2 is totally fine as an answer. But the inverse sine of -1, this is saying the y coordinate is -1. Because y, the sine part is the y. So when sine of t is -1, we're saying the y coordinate is -1. That's why it's minus pi over 2, because that works for both. Look, the x coordinate is 0 here, and the y coordinate is -1 there. That's why it's coming out of minus pi over 2. So t is equals to minus pi over 2 is the starting parameter value. And now we need the end parameter value. So for the end, I want 6 cos of t to equal 3. Cos of t to equal 3. And I want 6 sine of t to equal 3 root 3. And we solve each of those again. Cos of t is 3 divided by 6, which is a half. And sine of t equals 3 root 3 over 6, which is root 3 over 2. If you calculate those, you get t is equals to pi over 3. Both of them are positive, so you'll just take whatever the calculator tells us. It'll tell you it's pi over 3. So they were the start and end points of it. So C2 parameterized, we had 6 cos of t, 6 sine of t, minus 1, or t between minus pi over 2 up as far as pi over 3. They would be the parameter values for that. Tricky. But, I do any more of that. I don't think I'm going to do any more of that. I'll probably finish it off tomorrow. But it follows a very similar process to what we did the last day. So instead of, I'll just write it down, the formula for it. We want from A to B, there are parameter values. So we know for the line segment, it goes between 0 and 1. You're going to have to convert this in terms of t for both of them. And then you get r dash t. So we've worked out r of t for both cases. We want r dash t dt. That's what you're going to have to go down the road of for each of them individually. You've done them individually, you add both answers together. This would be r1 of t, let's say, would equal that line, and r2 of t would be the next one. I'm happy to stay on for another few minutes if you do have questions, but otherwise tomorrow, same that time in that channel. Why does the start point end up in minus pi? So because both of these things, maybe it didn't make that clear. I'll take that down again. 6 cos of t, 6 sine of t minus 1. And it was from 0 minus 6, 1, minus 1 to 3. I'll do one at a time. Okay, so at the start, this has to equal this. This has to equal this. And you can just read off that the z is the same, right? So I know 6 cos of t has to equal 0. And these things both have to happen at the same time. And this equals this. So these are simultaneous equations. They both have to happen at the same time. We can divide both sides by 6 in both cases. Normal equation stuff. So the word "and" there is a big thing, because you're saying that cos, and it's true, like the inverse cos of 0 is pi over 2, but it's also, so pi over 2 is that angle there, true? And it's pi over 2 because, as I said, like in just 2 dimensions, cos sine is your coordinate, like x, y. So cos is like the x coordinate, sine is like the y coordinate. So when you work out the inverse cos of 0, it's telling you the x coordinate is 0, and you're getting pi over 2 because any point along here, for example, 0, 5, the x coordinate will always be 0 up here. That's why the inverse cos of 0 is pi over 2, because it's telling you the x coordinate is 0 at pi over 2. But the x coordinate is also 0 any point down here at minus pi over 2. Right? So you do need to kind of take that leap into, yes, the x coordinate is at pi over 2, but it's also 0 at minus pi over 2. And this one then is saying the y coordinate is minus 1. Well, the y coordinate is not minus 1 at pi over 2, but it can be minus 1 and minus pi over 2. So this is the one that satisfies both of them. Remember I said they have to happen at the exact same time. They both have to be satisfied. Like t equals pi over 2 doesn't satisfy this one, because the y coordinate is not minus 1 at pi over 2. Hopefully that makes a bit of sense. So if you solve this one, sure, the calculator would tell you it's minus pi over 2 for this one here, which also works for this. If you type into your calculator the cos of minus pi over 2, you will see it's 0. Yes. I think you're typing in there. Hold tight. Oh, no worries. You're welcome. No worries. Okay, folks. I'll see you tomorrow. I'll do question. I'll finish off this. It's question 3. I'll do 5, and I think we'll do the other 6 as well. All right. Just because I don't think I explained it very well today. I blame me. Okay. See you tomorrow. Bye bye.
Bye.
No worries. You're welcome.